Good afternoon and welcome to our Perseverance Rover landing and watch party. I'm Lisa Hoover. I'll be your host this afternoon. We'll be watching the historic event streaming live direct from NASA. Thank you for joining us. And I already see that we have a lot of people watching us already. Why don't you in the chat tell us where you're watching from? Joining me from Chabot this afternoon is our Chabot experts, Gerald McKeegan. Gerald is a longtime volunteer and adjunct astronomer here at Chabot. He also serves on the Chabot's board of directors, and he's a member of the Astronomical Society. He holds a Master of Science degree in Space Studies and has over 40 years of experience working in the space industry, where he was involved in numerous spacecraft projects, including the Space Shuttle Cassini, the Mars Reconnaissance Orbiter, the Mars InSight, Solar Bee, Juno, and many others. In 1988, he was awarded the NASA Silver Snoopy Award by the NASA's Astronaut Office for his work in the support of Space Challenger shuttle. He also heads Chabot's near-Earth asteroid research with our observatory, and that work is done with our 36-inch telescope. Also joining us this afternoon from the Chabot team is Fareed Khalaf. Fareed is a retired career aviator with a passion for all things mechanical. His long life love of science has driven him to study the history of space science, rocketry, propulsion, and so much more. Welcome, Fareed. Our special guests this afternoon are Shanna Withrow-Maser, Aerospace engineer, and Winnie Kuang, mechanical engineer research associate, both from the NASA Ames Research Center in the South Bay here in California. And they are both involved with the Ingenuity Mars helicopter. Winnie Kuang is a mechanical engineer research associate with NASA Ames, like I said. She holds a bachelor's in mechanical engineering from UC San Diego. She's worked on the developing conceptual designs of the successor to the Mars 2020 mission's Ingenuity, the Mars Science helicopter. She also supports efforts for flight dynamics and controls the Urban Air Mobility, UAM, Mars Science helicopter and the Rover Craft Design Toolchain Workshop. So welcome, Winnie. Shanna Withrow-Maser is an aerospace engineer, also at NASA Ames Research Center in the South Bay. She graduated with her master's and bachelor's from Missouri University.
Lisa, can you press unmute? Lisa, you're muted. You might want to repeat the last.
Oh, sorry, somehow my computer muted there. All right, so we are, let me go back.
You just introduced Shanna, so.
Okay, great. So Winnie and Shanna are both going to do a special presentation, so you don't want to leave us, at 1 o'clock following the lander on their work on the Mars helicopter. And they'll be here to answer all of your questions live just after the landing. So why don't we give our guests just a moment to check in and tell us what you're most looking forward to today's mission. Why don't we start with you, Gerald?
Okay, well, I'm especially looking forward to the actual landing sequence. Landing sequence is all automated. Once the spacecraft enters the atmosphere of Mars, everything that it needs to do, and there's actually hundreds of things it needs to do, it has all happen automatically. It's about 11 minutes for a radio signal to reach Mars at this time. So you can't control it from the ground. You've just got to tell it what it needs to do and then hope the spacecraft does it all and that nothing goes wrong. So I'm really looking forward to that part. And, you know, when we get that signal that says Perseverance is safely on the ground, that's going to be the really exciting moment. You're going to see a lot of cheering and celebration at that point.
Fantastic. And Gerald, do you have a connection to this mission at all?
Yes, I used to work in the aerospace industry, and one of the companies that I worked for developed insulation that is being used on the spacecraft on the crew stage of the Mars 2020. So if you see photographs of the crew stage, which will be ejected before the spacecraft enters the atmosphere, but on that crew stage, you'll see some tanks that have what looks like gold foil on the outside. And that's actually material that we made at the company that I work for. And the specific gold foil that you see on there it's a variation on material that's been used in the past. And they had some special requirements for the spacecraft. So I designed that particular material.
Fantastic. Thanks, Gerald.
Yep.
Fareed, what are you most looking forward to in today's mission?
I'm looking forward to seeing the crew, the mission control crew, Adam Steltzner. I want to see how Babak Ferdowsi, also known as Mohawk Man, is sporting his hairstyle today. I haven't seen him yet. And I just want to see the excitement after a safe landing, like Gerald mentioned. And of course, I'm at a very high level of excitement right now. I may not show it, but it's there. So the whole mission's been exciting so far.
Thanks, Fareed, and welcome. Shanna, welcome from NASA Ames. Tell us, I know you must be like in anticipation of the helicopter. How do you feel?
Well, we're just so excited. You know, I'm live streaming and, you know, watching all of the congratulations and stuff already, the encouragement from the Ingenuity team as everybody's getting ready to land. And we're just all so excited as a team. And I think the thing that I'm most looking forward to is just, you know, we've been so focused in on the helicopter component that now, you know, we're getting to see everything pop up from the other teams and the other you know, the literally thousands of people who have contributed to this mission. And that's just so cool to be able to all celebrate together. So that's what I'm looking forward to.
Fantastic. How long have you worked on this project?
So I actually am a little bit of a late starter. I worked a little bit on the rotor test when I was a student, but I'm actually an early career at NASA. And so I came in and about 2 years ago, we started something called the Mars Science Helicopter Project, which is to develop the technology for the second generation vehicle. And that's actually how I got to know the Ingenuity team because it's the same group. And so I've actually been working with them since that project started about 2 years ago so that, you know, we already have the next mission ready to go.
Fantastic. Welcome.
Thanks.
And Winnie, welcome. What are you looking forward to this afternoon?
Yeah, I want to echo everyone else's response. I'm super excited about this landing. It's really a collective effort among all NASA centers and many industries. So, this level of excitement is just contagious, and I'm just so excited.
That's fantastic. I think we all are breathless with anticipation. During the event, we're going to be posting, for those of you who are kids and schools out there, some resources, some posters and activities that you can download and enjoy post-mission. So I'll be posting those on the Facebook live event so that you can grab those and enjoy. So back to you, Gerald. What's unique about this landing site, Jezero?
Jezero crater is about 28 miles in diameter. It's about 18 degrees north of the Martian equator. It's kind of in the border between a region called Isidis Planitia and Syrtis Major. And what's unique about it is that we think at one time, in fact, we're sure at one time, Jezero crater was a lake. About 3.5 million years ago, it was filled with water. That water came from a little river that actually cut through the rim of the crater and emptied into the lake. And right there where that river emptied into the lake, it created a delta region where sediment and debris that was in the river was deposited into the lake. And we're hoping that if there are any signs of life, past life on Mars, that would be a good place to look for it. So, that's one of the really exciting things about this mission. Unlike previous rovers, this mission is specifically designed to look for signs of life, past life on Mars. So that's why they chose this particular site.
Thanks, Gerald.
Sure.
So there are a lot of new features of this rover compared to some of the other ones. Can you tell us some of the differences this time?
Well, this rover, when you first look at this rover, it looks a lot like the Curiosity rover, which has been on Mars since 2012. Very similar design, rocker boogie wheel system, although it's a little bit more, the wheels are more robust than the ones on the Curiosity. It's got the mast and the head and the mast cam on it. It's got that robotic arm that's extending out from it. That robotic arm can extend about 7 feet out, and it has a turret on the end of it, which has all kinds of different instruments on the turret. The turret itself weighs 99 pounds, so you can imagine what it's like to extend that 7 feet out from the rover. But on that turret, one of the interesting things it has is a coring tool, which is something new. That coring tool is going to core into the ground. It's like a hollow drill, and it will dig into the ground and extract samples of the regolith in the surface of Mars and store those samples on the rover. And then a future mission, NASA and the European Space Agency will go back to Mars and bring back those samples back to Earth so they can analyze them on Earth. So that's one of the cool things. Another interesting instrument on the rover is called MOXIE. And, eventually we want to send humans to Mars, and humans need oxygen to breathe. We also use oxygen for rocket fuel. And so we want to be able to make our own oxygen when you're up on Mars. And so MOXIE is an experiment to attempt to make oxygen from the carbon dioxide that's in the Martian atmosphere. So those are just a couple of the new things that we have on this rover that we haven't seen before. This is the most sophisticated rover that we've ever sent to Mars.
Awesome. So another new feature, I'll throw this out to everyone. I heard that there's a microphone to capture sound.
There's 2 microphones. Right. Yeah, so one of the neat things that NASA does is they like to share these missions with the public. So, already you're able to watch the landing sequence as it's happening. But once the rover is on the ground and operating, all of the imagery that it's collecting is going to be available to the public on a NASA website. And you get all the raw imagery, the sounds picked up by the microphones on Mars. And, I'll let Sarah and Winnie talk more about this, but the helicopter has a couple of cameras on it as well. So when it's flying around, it's going to be taking imagery, and we're going to be able to see all of that as well.
That's great. And I heard the landing parachute is different this time.
It's a big parachute. It's 70.5 feet in diameter, and it will deploy. But one of the new things about it is that it's going to make decisions about exactly when to deploy. In the past, it just deployed at a certain time as the spacecraft was descending into the atmosphere. This time, the spacecraft has a lot more decision capability, so it will actually decide the right moment to deploy that parachute. And of course, it has to be a very big parachute. The atmosphere on Mars is only 1% of the density of the atmosphere on Earth. So if you walked outside without a spacesuit on Mars, you'd be walking into what feels like a hard vacuum. But there is some atmosphere there, and they have winds and clouds and so forth. But it's so thin that you need a really big parachute to lower the spacecraft down and continue to slow it down. It goes from 12,000 miles an hour when it enters the atmosphere to basically zero when the sky crane is hovering over the surface and lowering the rover.
I love that. It sounds like a smart parachute.
Yeah.
New technology.
Yep.
Really exciting.
There's a lot of new technology that's supporting the landing. There's the capability of actually steering the spacecraft as it's approaching its landing site. It can actually take images and compare them to images taken from a spacecraft orbiting Mars to select the best landing site. You don't want to land on top of a boulder or on the edge of a cliff or anything like that. So there's software and cameras on the descent stage that will actually pick the best spot to land and then navigate to that.
That's fantastic. So why don't we check in and see what's going on the NASA side with our live feed.
One of the questions I wanted to ask either Shanna or Winnie, the Ingenuity helicopter is underneath the rover right now. It's tucked up in a little enclosure on the belly of the rover.
And the auxiliary.
And it's the rover's gonna be there for a while before they actually deploy the helicopter. And I wonder if you have any sense of how long it's going to be before they'll actually deploy the helicopter.
Yeah, I can take a stab at that.
Right.
So we, of course, when we land, we want to make sure that everything operates as well as possible. And so we spend a really long time staying, right where we're at so that we can check out all the systems on both the rover and the helicopter. So the idea is that one of the first things that will happen once the mission is operational is that the rover will drive off from its landing site, and it will look and find the best flat piece of land that it can find for the helicopter. And we'll also make sure to be taking, data about the winds and things like that, so that we make sure that when we set the helicopter down, that it's as safe as possible for the flight window that we have. So that isn't exactly predetermined. It just kind of depends on how long those checkouts take and how long it takes to get those flight conditions we're looking for. But it's kind of estimated that it'll take about a month probably before the flights start.
Okay.
So early March-ish into April. And then we'll have about 30 souls or about a month to complete those flights.
That helicopter has a lot of off-the-shelf components on it.
Yeah, actually, a lot of the brain of the helicopter and the components is really similar to what's in your cell phone. So for example, like the accelerometer and things like that is just, what all of us have in our pockets that have been modified slightly.
Uh-huh. And have they been modified to withstand the environment on Mars? It's very cold on Mars. You've got a high radiation environment and all that. And I'm just curious how an off-the-shelf component is going to handle all that.
Yeah, so that's one of the really interesting parts about this mission. And one of the things that is already considered, as success, whatever happens over the next couple months, is just the number of commercial off-the-shelf or COTS parts that the team was able to use. And that really lowers our development time and things like that. But you're right, we do have to do a lot of additional testing to make sure that that hardware is going to be able to withstand the space component from the radiation, and especially the temperature side, because it does get so cold on Mars that we've had to do a lot of extra things to insulate the spacecraft and stuff, because it's not just a plane, like, it's not just a rotorcraft we would have here on Earth, it's also a spacecraft. So, there's a lot of work that's gone into that insulation and stuff to keep everything warm so those COTS components can work.
And this will be the first time that we've flown an aircraft on another celestial body. Is that right?
It's the first time we've attempted powered flight. So there's been some high altitude balloons that have flown previously, and Winnie will talk about that a little bit after the landing here as well. So I don't want to give too much away.
Okay.
Yeah, this will be the first powered flight on another planet, and it's also all solar charged, and it's also the first fully autonomous flight.
Outstanding.
Let's check in with our audience. What questions do you have for our experts this afternoon?
I assume you're seeing those questions, Lisa?
I am scrolling through. I'm gonna
getting lots of them, huh?
hop back over as soon as I get some here. Why don't we check in on NASA?
And while we're waiting for that, I just might want to note the first.
It's been great. I know I have a 9-year-old John at home, and he loves to draw the rover. And look at that. That is awesome. That's better than anything I could bake. That's for sure.
Yeah, so one of the first events that we're going to be looking forward to here is going to happen at 12:38 Pacific time, and that's when the cruise stage, which is the part of the spacecraft that's been actually sort of ferrying the rover to Mars, the cruise stage will separate from the aeroshell. The aeroshell is what contains the rover. And it has been attached to that cruise stage. And at 12:38 our time, that's when we will actually see the event happen. The cruise stage will separate from the aeroshell, and not too long after that, the aeroshell will enter the atmosphere. So 12:38 is the first major event of this entry, descent, and landing sequence.
Have ever asked. Are we alone in the universe, and where did we all come from? And by sending a rover to Mars, we are gaining evidence for the answers to these questions, more evidence than we ever had before. And I think that's so exciting.
It is. And I know you get loads of interesting questions from kids. Have you gotten any about Mars specifically?
Oh my gosh, yes. Everybody loves Mars. It's in movies and books and TV shows, and everybody loves Mars. So one of the things that I get asked a lot is that, it's called the red planet. Why is it red? Well, it's red because it's literally rusty. The top layer of soil on Mars has iron oxide in it, or rust, and rust has that brownish red color. So it's red because it's rusty. And also because it's red, they ask, is it red hot? Is it really hot on Mars? And well, no, actually, it's colder than the Earth. It's farther away from the sun. So as you would imagine, it's a little bit colder than the Earth. It also has a really thin atmosphere. So the heat that it does have, it has a hard time keeping in. And so it's a little bit colder. But then I also get asked, what would I weigh on on Mars? That's a really fun question. So on Mars, it's a little bit smaller than the Earth, so the gravity there is weaker. It's about 3/8 the gravity that we have here on Earth. So if you weighed 100 pounds here on Earth, you'd weigh 38 pounds on Mars, or 100 kilograms here on Earth, 38 kilograms on Mars.
Those are all super fun. I think even some adults want to know the answers to those questions, Emily. Now, why do you think it's so important to educate kids about science and give them that great foundation?
Well, science is the language of nature, and learning about science and learning how to think like a scientist means you are learning how to systematically seek out truth in the world. You are learning the scientific method, you're learning how to be a critical thinker, and honestly, those skills are great for whatever you end up wanting to do in life.
True. If you want to be a scientist or an opera singer, that holds true. And what are you most excited about today?
I mean, humans are launching a robot to Mars. That doesn't happen every day. I think in the hecticness that is going on today and all of the nerves, I just hope everyone can take a moment to sit back and remember that we live in a time when humans have the ability to send a robot to another planet. And that's so cool to me.
It is very cool, Emily. Take a deep breath. Thanks for joining us here.
Thanks for having me.
Sending it back to you now, Raquel.
Thanks, Marina. We are offering lots of ways to ride along with us to Mars. Now put yourself right into the action now with our Perseverance photo booth. You can pose next to the rover, place yourself in our mission control, and even see what you might look like taking a selfie on the red planet. There, you'll also have a chance to sign up to send your name to Mars on NASA's next flight to the red planet. It's all available at go.nasa.gov/Mars 2020 Toolkit. And joining us now is JPL Chief Engineer and Landing Veteran Rob Manning. He will be breaking down key moments coming up, and very few people know more about landing on Mars than Rob, going back to the Pathfinder mission in 1997. Thanks for joining us today, Rob.
Thank you very much, Raquel, for having me here. And what a wonderful experience. What a wonderful day for a beautiful day in California. We're just also excited here, anxious, worried, but very hopeful.
Rob, I have a question for you. There is a landing tradition at JPL that involves eating peanuts for good luck. Can you tell us how did that start?
Yes, it started in the mid-1960s. What happened was we had a series of missions that had failures. The Ranger program in the early 1960s, one after another, failed. And what happened was one day, a fellow by the name of Dick Wallace on Ranger number 7, on the 7th attempt, decided to bring peanuts to the ops area just before the launch, and guess what? That mission worked. Now, we're not supposed to be too superstitious. We're engineers and scientists after all, but we love tradition. And ever since then, before launch and before critical events like entry, descent, landing, we have brought out peanuts and shared them with the team. And it's been really a wonderful little experience. And so this is something we'll do. We're doing right now, and it's something that we just can't help ourselves. It's just part of the experience.
Well, speaking of the experience, how did the Perseverance team keep the tradition alive this year?
Well, this year we're passed out little packets of peanuts to the team, and they can sneak one peanut in their mouth as part of to keep the tradition alive. But you know, this is part of the COVID experience, but we can't leave this one undone. So this is what we're doing, and this is going to help us land safely.
All right, thanks, Rob. I have some questions for you a little later on.
Audience.
Heading back to
Why don't we ask our panelists a few of them? From Christopher, you've probably already covered the point, but we'd like to know how Perseverance differs from its predecessors.
Okay, well, Perseverance is very similar to the Curiosity rover that landed in 2012. Perseverance, the main body of the rover, is about 10 feet long, about 9 feet wide. It has a 7-foot-long robotic arm on it. So in that sense, it's very similar. It uses a very similar type of wheel system called a rocker boogie system. But it has a number of experiments on it and instruments on it that are different from what you had on the Curiosity rover. and rovers before these, the Curiosity and Perseverance, drew their power from solar panels. So they actually had solar panels on top of the rovers. But Curiosity and Perseverance both use radioisotope thermal generators. It's a system that uses small pellets of plutonium, which is a radioactive material. As it decays, it generates heat, and that heat is used to generate power. So the neat thing about that is the rover can operate all day and all night because it's getting its own power internally. It doesn't need the sun to produce power. The Perseverance rover has some instruments on it that are unique. I described one of them a little while ago, MOXIE, which is an experiment to attempt to create oxygen or extract oxygen from the atmosphere. The atmosphere on Mars is primarily carbon dioxide, and so this experiment is an attempt to extract oxygen from the carbon dioxide atmosphere and store it. Future missions, especially human missions to Mars, they're going to need oxygen. So this is an experiment to see how well we can make oxygen while on Mars. Another experiment that I described a little while ago is the coring device on the robotic arm, which will take small samples of the surface and store them. In a future mission, future NASA and European Space Agency mission will go back to Mars, another robotic mission. It'll go back to Mars and collect those samples. We don't have a date yet for when that will actually happen, but that's the plan, is to return to Mars with another robotic mission, extract those samples, and then launch them back to the Earth, bring them back to Earth, and analyze them on Earth. So there are some, there's an instrument on Perseverance that's specifically designed to look for organics. One of the primary missions of this rover is to search for signs of past life, maybe present life on Mars. That's why the Jezero crater was selected. So there is an instrument that specifically will look for organics on Mars. And that's a little different from previous missions. Previous missions were not so much about finding signs of life as they were about studying the composition of the soil, what we call the regolith, and the geology and the climate and so forth. This instrument is the first time we've gone there specifically to look for life. I think the last time we did any kind of a life searching experiment was back in the days of the Viking landers. So this is a new instrument that we haven't seen before. So that's just a summary of some of the things that are new on this rover that are different from the previous rovers.
That's great. We have a question from one of our 5th grade viewers, from Jason. He says, say life is found, then what?
Yeah, then what? So there are some protocols that NASA has about being very careful not to contaminate the environment on Mars. So if we find signs of life on Mars, we don't want to contaminate it with microbes or bacteria from the Earth. So the spacecraft is very sterile. And if we find current life on Mars, that's going to implement a whole set of protocols that NASA has about protecting and preserving it, and how we will deal with it if we decide to send manned missions there. So, and the most exciting thing, of course, is, hey, we've found evidence of life on another planet. Most astronomers, space scientists are fairly convinced that there is life out there in the universe. We just haven't found it yet. So if we do find life, it'll be the first time we've shown that life can exist on other planets, and that will be pretty exciting.
It's exciting indeed. Another question while you're on the mic, Gerald. Jim says the gold-colored material on the spacecraft, is it actually gold?
No, it's not. It's actually a plastic material It's called Kapton. And Kapton, if you saw a piece of it, it would look like a thin film, a little bit thicker than a piece of saran wrap. And it's transparent, but it's amber in color. So if you just take pure Kapton and look at it, you can see through it, but everything you see would be amber in color. And to give it that gold appearance, they coat one side of the Kapton with aluminum. And I see Fareed's got one of my samples that I sent him. And so one side is coated with aluminum. And so that side is very shiny. It's almost mirror-like. And you see Fareed is unfolding a piece of it there. So the aluminized side is like a mirror. The other side is just the Kapton. And as you look through the Kapton, you're looking through it because it's transparent to that reflective layer. And that's what gives it that gold appearance. So it's actually plastic coated with aluminum. Now there are many different ways of doing this. The one way that's on the tanks on the cruise stage are actually kind of a unique configuration for doing that. It has to be reinforced. It has to have certain properties that were essential for this spacecraft. But some variation of this has been used, going all the way back to the Apollo days.
Fantastic. We have a couple of related questions from Stacy and Gary. They're asking about the life expectancy of both the rover and the helicopter. Maybe I'll throw this to the NASA team.
Yeah, so I can address specifically the life of the rotorcraft. So our job with the rotorcraft is to do a tech demonstration this time. We'll hopefully, as long as we're successful, we can build on that. We'll have future missions where the rotorcraft is more central. But it was so nice of the rover team to let Ingenuity tag along as part of the payload. But that means that if we're using Perseverance as cameras and instrumentation and stuff to watch the rotorcraft, then Perseverance can't do its main mission. And so, that was a great, example of collaboration that the rover team was willing to do that and willing to let the rotorcraft tag on to its launch that was already scheduled. But in respect of that, we'll have about 30 souls once we start our flights to finish our mission. And then we'll go ahead, and even if the rotorcraft could continue to operate, we'll stop operations at that point so that the rover can continue on with its mission.
All right, we're getting really close to our first landing sequence event at 12:38. We're going to have the cruise stage separation in about a minute here.
Right. In about a minute and 20 seconds after that, the spacecraft will do what's called a D-spin maneuver. Right now, the spacecraft is rotating at about 2 revolutions per minute, and that's to make sure that it gets kind of even exposure to the sun during the cruise from the Earth to Mars. And about a minute and 20 seconds after cruise stage separation, it will stop the spin. There are some little thrusters on the back shell, and it will stop the spin. So that will happen at about 12:39 and 20 seconds. And then at 12:40, the spacecraft is going to eject some of the balance masses that are used to keep the weight distribution of the aeroshell nice and even. Because it's rotating, you want to have the weight distribution nice and even. It's like balancing the tires on your car. So there are some weights that are currently on the cruise stage that, or on the aeroshell rather, that will be ejected to because they don't need it anymore. Also because they want to have the aeroshell at a certain angle as it enters the atmosphere, and so they'll get rid of those masses at about 12:40.
We're continuing to receive tones from Perseverance, standing by for cruise stage separation.
Yes.
We have indication that crew stage separation has been confirmed by the spacecraft.
We're off on a good start.
In about 1 minute, Perseverance's landing software will wake up and begin the final preparations for entry. The first action it will do is to fire warm-up pulses with its entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
Okay, so now the vehicle's on its own. It's turning itself into the direction of facing the heat shield toward Mars, and will eventually hitting the top of the atmosphere. We're not far away. This is going to go very quickly from here on out.
All right, we're getting close.
That's confirmation that we got shadowed by the cruise stage as it passed through our beam to the Earth.
Telecom indicated actually that we could see a signal that the crew stage went between the Perseverance entry capsule and Earth. So we saw a little blip, the data stream indicating the crew stage separation.
So atmospheric entry should happen about 12:48.
Up those entry thrusters. Warm-up pulses have begun.
All right, we'll see if we can squeeze in another question or two.
The spacecraft is trying to stop its spin from the cruise 2 revolutions per minute down to 0, and then we'll turn to its desired orientation from
So we have a couple of questions about the core samples. When they will be returned to Earth, and how deep the core is going.
Okay, the return date has not been established yet. NASA and the European Space Agency are planning a future mission, but I don't believe they've actually set a date yet for when that mission will occur. They can only launch to Mars every 2 years and 2 months. So this launch occurred in July of 2020. The next launch window is in September of 2022. And then the next one after that is two years and 2 months later, and so forth. So one of those future launch opportunities is when it will happen. And I'm not aware that they have actually set a date. As far as the core samples are concerned, they're about not quite 2.5 inches long and about a 1/2 inch in diameter. So I was reading something from NASA. They describe it as looking like a piece of chalk from your school chalkboard. I guess nobody uses chalk anymore on chalkboards, but in school. But that's what it would look like. And there will be several of these that it will extract. They have a little container that they'll put it in, and then they'll store it on the rover for future retrieval.
Awesome. A question for the NASA team. How will the helicopter deal with the atmosphere and I imagine the windy conditions of the planet?
Oh, so I can answer this one. So there has been extensive testing done at JPL and various NASA centers to ensure that the Mars helicopter can fly. But of course, we're waiting to see actually how it can perform as a flight demonstrator.
And a follow-up question. I heard the helicopter pilots joke that their craft rotors beat the air into submission to stay aloft. How do they adapt the rotors to work in the lower gravity?
I'll grab this one. So the lower gravity is actually helpful to us because it means that it's easier for us to get off the ground. It's really the low density of the atmosphere that makes it difficult to fly because it's only 1% as dense on Mars as it is here on Earth, which means it's a lot more difficult to, like they said, beat the air and generate the lift. So yeah, we did have to do a lot of designs and your design changes, and a Mars helicopter isn't going to look the same as maybe the drone that you fly around your backyard. It's going to have a lot larger rotors for one thing, and then they're also going to be shaped differently. So that's just a couple examples of some of the changes that we made, but it was definitely a very extensive effort to try to optimize those.
Yeah, I want to add that. Oh, there has been extensive design of the airfoils. Research on what type of airfoils perform best in Martian-like conditions, and also the composition of the airfoils. They're a lot lighter. They have a foam core and carbon fiber skin.
And the helicopter itself only weighs 4 pounds, right?
Yeah, it's about 2 kilograms. So it's easy to just lift up with one arm. And yeah, it's a much different vehicle than what you would expect to find here on Earth. But you still have to fit all of that, really robust landing gear and all of that, protection for launch equipment and things like that on it. The other thing is that the rotors are a lot stiffer than you would find in a traditional rotorcraft, and that helps us be able to control it as well.
I could add something. I like to think of it as an aircraft with the wings from an albatross that move like a hummingbird's wings. And they need to be larger to compensate for the thin atmosphere, and they have to move a lot faster. At 2,400 RPMs, I imagine the tip speeds are close to the speed of sound in that environment. So.
Great. We have another question from one of our young viewers, Molly, who's 8. She's watching from Montana. She wants to know, how will you recognize life? And is it really different from us, like an alien that looks like a rock and doesn't move or talk or breathe?
Well, what we're going to be looking for is life that's something like life on Earth. So organic compounds. Life on Earth has things like amino acids. And so what we're looking for is life that's similar to life on Earth. If you have life that's totally exotic, completely different from anything we have here on Earth, we may not be able to find it, but certainly any kind of life that's like life here on Earth, that uses the organic chemistry that we encounter here on Earth. Like I say, I'm sure you've all heard about protein. Protein is composed of amino acids, and we know there are amino acids out in space. So the question is, do we find them chained together to produce proteins? Or do we see processes that chemical processes that can only be done by life? And so those are the things that we're going to be looking for.
Yeah, on the original Viking probes that were not roving, they just landed and stayed put and did all their experiments under their own landing gear, within reach of the scoop that picked up some Martian soil and put it in a container. And then from Earth, they delivered a very nutrient-rich soup, so to speak, to mix with the soil. And in the presence of microscopic life forms, it would produce biological gases and byproducts, which they were looking for. And I don't believe they found any then. And that experiment is detailed in Carl Sagan's Cosmos, both in the book and the TV series. And a friend of his, Wolf Vishniak, designed that experiment. And he was out in the field, and I believe in Antarctica, when he fell into a crevice, and unfortunately.
Yeah, we've got another event coming up here. This is when the entry interface officially happens. And that's when the 7 minutes of terror starts. So that should happen here momentarily.
We have confirmation that the Mars Reconnaissance Orbiter is now relaying data from Perseverance. We're about 30 seconds from entry interface. Perseverance is going about 5.2 kilometers per second and is about 190 kilometers altitude above the surface of Mars.
Confirm your eject data flow.
About seconds from entry interface. 5.3 kilometers per second and an altitude of about 150 kilometers from the surface of Mars. We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars. The spacecraft is now waiting until it begins feeling the atmosphere of Mars to slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target. Navigation is also confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
The vehicle should be doing its turns right now.
MRO has lost lock.
Perseverance. We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
Answer a question. The images you see are computer
We saw a
graphics.
small
They're
outage
not,
of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target.
At about 12:52, it will do the Super maneuver, straighten up and fly right. It'll eject 6 masses, weights.
Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target.
So the Super maneuver is to change the angle so that it's going basically pointing straight down instead of at an angle. That's coming up here any minute now.
So we're waiting for the jettison of the
Our
ballast.
current velocity is about 550 meters per second at an altitude of about 15 kilometers from the surface.
And we're about 1 minute away from parachute deploy. The exact timing of the parachute
MRO is reporting good telemetry lock.
is determined by the spacecraft itself.
We're coming upon the straighten up. We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Yes, yes, yes.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
And the heat shield should separate here in about 10 seconds.
Yes.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
The terrain navigation system is now directing the spacecraft toward an optimum landing site.
Yes. Yes. Yes.
Perseverance now has radar lock on the ground. Current velocity is about 100 meters per second of the surface of Mars. Perseverance is continuing to descend on the parachute. We're coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Almost there.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Yes.
We have priming of the landing engines.
So the sky crane is now lowering the rover.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars.
So the sky crane will stop in a second,
We have
hover
started our
and lower
constant velocity
the rover.
accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
As expected. As expected.
Sky crane maneuver has started. About 20 meters off the surface.
It's down.
We're getting
It's
signals
on the
from
ground.
MRO.
UHF is good.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life. At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
This is so exciting. Let's see some excitement in the chat. We
Yeah.
made it.
Yeah.
Congratulations, NASA.
They're still getting telemetry from the lander.
It's really amazing to think about all of the things that had to happen autonomously while this was going on.
We're going to wait for the
And
image.
once again, NASA has succeeded.
This is so exciting.
This
The
is the
team is
5th rover
beside
that
themselves.
NASA has
It's
landed
so
successfully
surreal.
on Mars.
Stay tuned. We might get some pictures.
Great.
This might be a good chance for me to mention that next month, on the 26th, which is a Friday, at 7 p.m. on Chabo's featured presentation for that evening,
writing on
be
this.
talking about a landing phase rate.
Yeah, we
So
just
I
heard
can
the news
explain
that
how knuckleball becomes a
Perseverance is
curveball
alive on
after
the surface of
jettisoning the
Mars.
ballast. So bring all your questions.
Flight, we have seen the completion of EDL 3000.
Well, folks, this is not the end of the mission. It's only halfway. The rover has a lot to do. The helicopter has a lot to do. And don't forget those core samples. The science
MRO still seeing a
continues.
strong signal from the lander.
As we make the transition here, it might be a good opportunity just to take this moment and ask for your support of science and STEM education with the Science Center. Your donations fuel science programs,
We've just heard the
helping
news
us
that
promote opportunities for all. So there's a red button in the chat on Facebook where you can make a contribution. And some of you have already done. We've seen you. Thank you so much. We know that there are far more questions that came in that we'll probably be able to answer today. But just in about a minute here, we're going to turn over the program to Winnie and Shanna, who are going to give us a presentation about their work with the Mars helicopter. So any last thoughts on the landing before we make that transition?
One comment I wanted to make, Lisa, while you're waiting for questions there, you may have heard them referring to MRO several times. MRO is acronym stands for Mars Reconnaissance Orbiter. It's a spacecraft that has been orbiting Mars for several years, and it has a very high resolution camera on it, and it acts as a relay station. So the rover is sending signals to MRO, which then transfers those signals to Earth. And one of the things that I'm hoping they were able to do, MRO has a very high resolution camera. And when Curiosity landed on Mars in 2012, they were actually able to capture an image of the rover as it was descending on the parachute. And I'm hoping they were able to do that again this time around. So that'll be exciting to see.
Also on the world stage, there was a slight traffic jam on Mars over the last 3 days. 2 other countries took advantage of the alignment of the planets for the launch window and sent their own spacecraft. So United Arab Emirates is one, the other is China, and we're the last of the trio to complete the landing phase successfully. All missions have been successful so far. So look into those, they're interesting.
Yeah, the United Arab Emirates spacecraft is called Hope, and it's an orbiter. And then China's spacecraft is called Tianwen-1, and it's actually has a rover on it as well. But right now it's in orbit, and they're not going to land the rover until later on this spring. So exciting time. And all of these spacecraft launched within about 2 weeks of each other. And that's because of that launch window that I was talking about earlier. You only can launch every 2 years and 2 months.
That's great. Well, as we swiftly make our transition here, fun fact from NASA, Perseverance and missions like this build on NASA's Mars legacy of orbiters, landers, and rovers, 9 to land and 5 to rover. Way to go, NASA. Keep it going. All right, Winnie and Shanna, are you ready to take the helm?
Yeah, we're ready.
NASA's always ready.
I will share while we're pulling it up that I had the privilege to get to be in on the Ingenuity team feed as well. And we just got confirmation that all of our batteries and such with the last ping that we got are charged like they're supposed to be, and we'll be getting our health data from Ingenuity tomorrow. So
great, that's good.
So hi everyone, my name is Winnie, and I'm here with my colleague Shanna Withrow-Maser, and we're both engineers at NASA Ames Research Center's Aeromechanics branch. Can you change to the next slide? Today we're going to be presenting about NASA Ames Research Center's aeronautics contributions to Ingenuity Mars helicopter. Next slide. We're going to begin by talking about our NASA experience. Next slide. So, as Lisa mentioned, I have a background in mechanical engineering. That's what I studied for my undergraduate. And right after graduating from college, I got an internship opportunity to work at the Aeromechanics branch. I feel incredibly lucky because my main project at the time was working on the Mars Science helicopter, which we'll talk about more later. And my project was involved in developing conceptual models for the Mars Science helicopter, which is the successor to the current Mars helicopter Ingenuity. And this Mars Science helicopter will have a focus on scientific missions, unlike Ingenuity, which is for flight demonstration. And another area that I worked on is related to rotorcraft vertical lift technology. So there's been growing interest in rotorcraft because of its capability to vertically lift and land. And this will be very useful as a means of transportation in urban environments. So NASA has a lot of very powerful rotorcraft design software, and we are passionate about sharing our resources with the public. So the Aeromechanics branch hosts workshops throughout the year to teach the public on how to use these software and design rotorcraft. And another project that I worked on, which is related to this, is on assisting with tasks for the flight dynamics and controls team, which Shanna is a part of. Next slide. And here are just some pictures that I took throughout my time at NASA. Much of these pictures are taken while I was an intern. And as an intern, it was great. I had the privilege of visiting multiple NASA centers, including NASA Armstrong and NASA JPL. In the middle, we have NASA Ames' largest wind tunnel, which is the largest wind tunnel in the world, the 80 by 120. And I was assisting some of our branch members in recording an experiment in the wind tunnel. And lastly, we do have exciting talks every now and then from renowned researchers on campus at Ames. Next slide.
Thanks, Winnie. So like as was said before, my name is Shanna Withrow-Maser. Can we actually go back a slide? Perfect, thank you so much. And I get the privilege of working at NASA Ames, which is just a really cool area. And one of the things that I wanted to highlight for you guys is, you know, we are so excited as a NASA team. You know, this was a joint center effort. There, you know, most of the centers contributed to this mission that we're talking about today in some way, shape, or form. So congratulations, you know, to our JPL colleagues as well as our colleagues at the other NASA sites. Today, we're going to specifically focus in on the work that NASA Ames does, and that's because for many of you watching, NASA Ames is in your backyard. You know, we're just south of San Francisco, right in the middle of Silicon Valley, and so that's really cool because it's not like this stuff is happening a world away. It's happening, you know, right here in California. So I was fortunate enough to get to join the branch as an intern, as a student in 2014 and 2015. And then I entered something called the NASA Pathways program, which let me finish my schooling actually while I was working at NASA and then convert into a civil servant position. So now that I'm a civil servant, I work in our controls group and then I work in our vehicle design group. So with the controls group, I work also on our urban air mobility applications, which is some of what you see here. And so we get to use some really cool test facilities. And so this one's kind of like a roller coaster track that we put pilots in, and we put pilots in that white cab there on the right side of the screen, and we allow them to test out the vehicle controls. And we use this facility to like train shuttle astronauts and to test out new flight configurations before we actually put them up in the air. So that's pretty cool. And then as the Mars Science on the Mars Science helicopter team, I get to wear a lot of hats. I work in the controls group, I work in the design group, primarily on the packaging of the vehicle, just like you guys saw, so that we can get it to land like we just did for Ingenuity. And then I'm also the vehicle assistance lead, so I make sure that, you know, all the different groups are talking together and the systems can interface well together for the vehicle. And then I act as a liaison between Ames and JPL to make sure, you know, that all of our scientists and engineers are on the same page and work with my counterpart over there. Next slide, please. So here's just a couple other activities. One of the best parts about working at NASA is just that there's always tons of tests going on, and it's very much a, you know, as needed kind of job, additional tasks as needed. So, you know, even though those are my main areas, I also get to work in the wind tunnels with the full scale models and do collect data in the Aeolian wind tunnel, which you can see the rotor there at the bottom, which lets us collect data for Mars. And then the favorite part about my job is actually mentoring the students. It's just so fun because they come, you know, from all over the country and all over the world, and we get to work on diverse projects. One of my favorites that they've done recently is you can see the little bot in the right-hand side was a model that they were working on to be able to transfer some software over so that we could apply some of the research we've been doing to search and rescue vehicles to help with the local wildfires. So that's pretty neat. Still just in the beginning stages of that, but really cool projects that the students work on. Next slide. So, you know, we just talked about Perseverance and we talked about Ingenuity, but I'm sure, you know, you're wondering why do we want to fly on Mars other than just, you know, it's really cool to be able to fly on another planet. What is the long-term goal? Next slide. So there's a lot of science that we can do on Mars with the type of vehicles and the instrumentation we have. But when we start to be able to use a rotorcraft, we can do a lot more science over a lot wider regions. And that's mostly because we can get a lot closer than an orbiter, and we can cover a lot more terrain than a rover or a lander a lot faster. So some of the specific science we're interested in is things like geological mapping and stratigraphy, volatiles and climate, astrobiology, atmospheric science, alien and slope processes, and geophysics. And some of those we can do with the instrumentation we currently have, but you'll see over on the left that these are each areas that are either enabled or the type of science that we can do is increased by aspects related to the rotorcraft. So because of the rotorcraft's range, we can enhance the ones that have the green dot by them. And that's the same for the purple, for the rotorcraft's access to hazardous terrain or access to the planetary boundary layer, which is in blue. Next slide, please. In addition to just the types of science we can do, we can also look at more rotorcraft sites. Right now, we're kind of limited to the flat spots where the rotorcraft or the rover can easily land and then move around. But if we have a rotorcraft, we can fly up and over some of those ground-based barriers. So we can then study things like canyons, poles, caves, skylights, like you see here on the right, and also potentially land at higher altitudes, which is where we kind of suspect some of the really, really interesting science data may be collected. It'll also help us as we prepare for human exploration of Mars because, for example, the caves might potentially be a good candidate to help shelter the astronauts, but we won't know till we are able to check them out. Next slide. And I'll hand it back off to Winnie for a little bit of history.
Yeah, so I'm going to be talking about the history of the Mars helicopter. Next slide. So the concept of a Mars aerial vehicle has actually been around for some time, since the mid to late 1900s. And that was due to the success of the Viking 1 and Viking 2 missions to Mars. Now, one thing to note, as Shanna mentioned earlier, aerial flight on Mars has been done before. And the Soviet Union, back in the late 1900s, they launched through their Vega mission an atmospheric balloon that was able to fly in Venus's atmosphere and collect some data. So these concepts of Mars aerial vehicles has been around, but the efforts have been sustained. It wasn't until 1997 that Ames received the Center Discretionary Fund effort, where these efforts actually got pushed. Next slide. Here is a graph just showing you a rough idea of the wide range of concepts that have been developed related to the Mars airplanes. On the right side, you can see a graph. You can see that different propulsion types were examined, and you have the total vehicle mass plotted with the flight range. And one of the general trends that I want to point out is that initially, missions or concepts were quite ambitious, planning out vehicles that were larger with longer flight times. But over time, there were advancements in electric propulsion, which led to smaller vehicles. And you can see that with more recent Mars airplane concepts, we're looking at smaller sizes. Next slide. Here are some of Ames' contributions to the Mars airplane concepts. We have the AIM and the MAGE and the Canyon Flyer. And at this point, we also consider looking at airplanes with propellers. Now, propellers are very similar aerodynamically to rotorcraft, but another thing to consider is that rotorcraft has the advantage of vertically lifting and landing and working in conjunction with solar arrays and electric propulsion. So that naturally led to a transition in rotorcraft Mars technology. Next slide. And as I mentioned, 1997 was when Ames received the Center Discretionary Fund effort. And from that point onwards to the early 2000s, Ames was focused on critical technologies. So looking at the aerodynamic performance of rotors in Martian-like conditions. In fact, Ames was the first to document a hover test of a rotor in such conditions and also could perform computational fluid dynamics. During that time, Ames also had a surrogate rotor model, a helicopter, fly in Devon Island, which has a very similar terrain to Mars, which is really cool. And in 2014, JPL proposed Ingenuity as an aeroscout for Perseverance, for the Mars 2020 launch. And this launched the collaboration between JPL, NASA Ames Research Center, and NASA Langley Research Centers. On the bottom left is the kickoff meeting that JPL had with NASA Ames. Next slide. So this slide highlights the key members that were part of the Mars helicopter development. But of course, there are more talented scientists and engineers. One thing that I really want to note is that some of these key members are early career folks, so really young engineers who have just finished their college education. Our branch, the aeromechanics branch, likes to host young engineers who are still studying in college, and they had the chance to also contribute to the Mars helicopter project in various ways. Next slide. And this is just a timeline showing the amount of effort that was done to make this Ingenuity concept possible and be a working helicopter that has landed on Mars in just 6 years. So there's a combination of testing out the rotors, experimentally testing out the rotors. And when you design anything, experiments and simulations go hand in hand. So there is also a lot of computational fluid dynamics analysis done on the rotors. But one thing that I really want to stress is that this is all novel work. So some of the facilities that we currently have right now need to be changed to accommodate this kind of research. And there also needs to be research done on how to make this, the facilities that we have to be better able to conduct experiments in. And you'll notice that towards the latter portion of this timeline, there has already been work on the Mars Science Helicopter. And as we mentioned, that is Ingenuity's successor. Next slide. So I'm going to hand this off to Shanna.
Thanks, Winnie. So now I'm going to give a little bit more specific about the Ingenuity helicopter, what it looks like, and what it's going to accomplish. Next slide, please. So a little bit of background. The Mars Helicopter Tech Demonstrator was the original name of the helicopter, and it became Ingenuity. And it started around 2014. And as you all just saw, it launched along with the rover. You can see here on the picture of the right, the team at JPL integrating the rotorcraft into the bottom of Perseverance, where it was stowed for till it deploys here in the next few weeks. And the goal of this is to demonstrate flight for the first time on another planet. Next, please. So this is a little bit of what Ingenuity looks like. You can see, it's not that different from what you might potentially fly around your backyard. We have antennas up at the top that allow us to interface with the rover, and then the rover, transmits that data back to Earth. That little solar panel on top, that square thing, allows us to collect enough energy not just to fly, but also to stay warm all throughout the cold Martian night. We have our avionics stored there in that square thing, which is the fuselage or the body of the helicopter, which tells it how to fly and where to go. We have an altimeter and cameras there that help it to fly, also in that box. The legs are, so that we can land on the surface, but the one thing that's really special about them is how light they are. Additionally, in that box, we have batteries, like any other spacecraft, and then the blades. And what's really interesting about the blades is that they're actually just made of carbon fiber with a foam core. Next, please. So Ingenuity, now that they are officially on the planet, which we are so excited about, over the next month or so, they'll do checkouts on both the helicopter and the other instrumentation that's on the rover, as well as the rover itself. And then when they decide that everything is working as desired, the rover will pull off from its current landing site, and it will use an arm to drop off Ingenuity as soon as we determine that it's safe, and that we have a good window weather-wise and such for the flights. And then we'll attempt 5 about 90-second flights of increasing difficulty. So, at first we might just try to hover, and then after that, we'll try to go further and go for longer. It's a 2-bladed coaxial helicopter, so it has 2 blades that counter-rotate, which allow us to control it. And like I said, this is something that you could probably fairly easily pick up. The rotor diameter is about 1.2 meters, which is about 3 feet, possibly approximately your wingspan. But I will say that it's a lot bigger rotor than what you would expect to lift the same volume here on Earth. So the payload itself is only about a softball size. So that's one of the things that's really different. The power is all solar related, and then we fly, and then we take about 1 to 2 days, or Martian days, which are sols, to recharge so we can fly again. Next, please. Thank you. So what are some of the challenges and what's unique about flying on Mars? We keep saying it's hard. Why is it hard? Well, because of the communication delay, we can't interact with it while it's flying. So everything has to be autonomous. In addition to that, because the air is so much less dense on Mars than it is here on Earth, normally rotors have some flapping motion, and that's a good thing. That helps us be able to control them. But on Mars, it's not dampened at all by the air. And so that can make it a lot easier for the vehicle to go unstable. Additionally, like we said, this is both an aircraft and a spacecraft. So we have to make it light like an aircraft, but robust enough that it can withstand launch and entry into the planet and things like that. And then lastly, the aerodynamic performance is different, again, because the air is so thin. And it's a lot colder. Next, please. And I'll switch back to Winnie.
So here, I would like to make a note that since Shanna and I are part of the aeromechanics branch, our background is in rotorcraft, but NASA Ames has contributed to the Mars 2020 mission in many ways. So one of the points that I want to bring up about their contribution is NASA Ames has tested the parachute that they use for the Mars 2020 mission in the A by 120 wind tunnel at Ames, which is the really large wind tunnel. NASA Ames has also contributed to the testing of the heat shield in one of our facilities, and has also developed sensors that go on the aeroshell. So as you saw earlier in the live stream, the aeroshell is what is holding all the spacecraft inside, and that's what is used to protect the spacecraft from the forces and the heat from entering into the Mars atmosphere. So next slide. So as you saw in the previous timeline, there has been a lot of effort to make this ingenuity possible. And much of the efforts done on the rotorcraft side related to this project is rotor design, designing the airfoil and characterizing the airfoil through simulation and experiments. Also experimenting with the rotor and seeing how well it performs in Martian-like conditions. And you saw in Ingenuity, as Shanna mentioned, there is a solar array on the top. And we've done analysis on characterizing how a solar array will influence the rover during hover and what is the appropriate size of the solar array. And lastly, we also have tested the first ever surrogate of the Mars rotor in forward flight in one of our facilities in the N242 tunnel. So next slide. So this is a visual representation of my last point. We have the surrogate rotor on the left, and the bottom is the wind tunnel in the Planetary Aeolian Laboratory at Ames. And on the right hand side, we have, whenever you conduct any experiments, it's good to benchmark it with simulations. So here we have what is a ROT CFD simulation of how the rotor will perform based on simulations. So next slide. So one thing that I wanted to note is that you learn a lot from experiments. And one of the things that we learned from the past experiment that you just saw is that there were significant aero interference effects that is an outcome of testing in a facility. So this effect is recirculation of the rotor. So the air from the rotor is recirculating because everything is tested within a chamber. So because this is all novel, we then conducted more tests to characterize this flow recirculation and see how we can mitigate the effects of this type of recirculation on future experiments. And this was done at JPL's 25 space simulator and other NASA large vacuum chambers. So this experiment was called the weather test. And from this experiment, we were able to get a time-dependent analytical model, which was benchmarked with computational fluid dynamics results. And this wind model was used for future studies. Next. This is a visual representation of that experiment that I talked about. On the left-hand side, it's kind of hard to see, but the rotor is inside the box because just to protect the rotor, that is propped by the white stand. And there is a wind sensor right above it. So the left-hand side is a visual representation of the flow, and this is done by fluorescent lighting. Next slide. So as I stressed before, this is all new. So some of the facility that we have right now needs to be developed to better accommodate testing under Martian-like conditions. In our effort with various NASA centers and JPL, we've developed different approaches to handle testing of the prototype in Mars-like conditions, including the swinging arm approach, just to simulate the vehicle hover in response to winds. So Shanna's going to talk more about it later, but this involves attaching the prototype of the helicopter on a swinging arm, and this swinging arm will, there's my hand, will move in a circular motion, and that is to simulate the response to winds. Shanna's going to talk more about this later, but we've also done a lot of testing related to system identification to understand just aerodynamics-wise, what are some of the fundamental properties. And also there are also multiple approaches, including developing custom wind tunnel tests and such. Next slide.
Thanks,
So
Winnie.
I'm going to hand them. Oh, yeah.
So like Winnie just said, you know, we don't have a previous case to work off of, and it's not in a textbook anywhere that, you know, tells us how to develop these models. So not only does NASA work as a whole and collaborate among the different centers so we can get the different expertise group, but we also go out and, you know, talk to industry and lean on the strengths of those as well. So as well on our collaboration team was a company called Aerospace, which, you know, really helped in development of the rotors as well. And that's really cool to kind of take the best from each groups and have everybody work together. So one of the things we needed to do was, you know, we thought we had a general idea of how to control the vehicle based on our calculations that we did, but we really didn't know until we tried it. So we did this thing called System ID, which let us kind of figure out if the calculations we were doing matched what we expected to happen. And so we did that by, you know, taking that vacuum chamber and putting an arm in it. And the reason we did that is because we needed to simulate some of those forces that the rotorcraft would experience as it was flying. But, you know, we needed to do it in special conditions. And so between the swinging arm and then also a wind wall that was made up by a bunch of fans, then we were able to kind of simulate some of that motion and turbulence that the vehicle will experience on Mars. Next one, please. Thank you. So here's a quick demonstration of why it's important to do this. So this was one of the very first tests, if you don't mind going ahead and playing the video, that shows, you know, a prototype of Ingenuity's first attempts to fly in this type of environment. So as you can see, it's attempting to hover here and it's getting off the ground, but we're not being able to control it very well. And it's becoming more and more unstable. And then that happens. And that's why we need to do this testing. Because of course we only get one shot on Mars, and like we don't want to waste that. So that's why, you know, we do hours and hours and hours of testing ahead of time. Next one, please. So after some adjustments, oh, I think this is the same one. So after some adjustments, we came up with this refined design, and we had to try to offload as much of the mass as possible to account for the difference in gravity in the chamber. And then after that, we added these white targets up on the top. The Ingenuity team did in order to be able to put sensors in the tunnel and then sense where the rotorcraft was as it was experiencing these different forces. Next one, please. So again, we kind of started with modeling and simulation, then we did the system identification, and you can see the picture here of the rotorcraft on the arm we've been talking about, redesigned the control system, and then that let us get to some free flight experiments, which you'll see on the next slide. Oh, forgot one. So the other thing is just that, you know, we started with the basics of a fixed frame, then we added in the dynamics of the robotic control, and then the gimbals dynamics as well. Next, please. Okay, so then this is what we finally got to. And as you guys can see, it has to spin really, really fast. So that might not look like much if you were just flying a drone in your backyard, but for the Ingenuity team, when the rotorcraft did this, it was extremely exciting because it meant we had figured out how to control it in that environment. The reason it's spinning so fast is so that we can generate more lift. Okay. We can go ahead and move on. Yep. And And then we took that data that we gathered from that text, and then since we had something we could kind of match in a relevant environment, then we were able to do a lot more extensive simulations and, you know, simulate the entire Mars environment with, you know, the gravity and the winds, and try a bunch of different combinations and make sure that throughout the duration of the flights that it would be doing, you know, that it would still be stable and be able to fly. And so that looks a little something like this. Do you mind starting the video? Perfect, thanks. So this is a little bit more like what one of the Ingenuity flights will look like. You'll notice we take off and we hover, and you can kind of see in the bottom corner what the Ingenuity's cameras, you know, will simulated through simulation what they'll be seeing. And here you'll see we're yawing a little bit. And we land, and that's about it. Next slide, please. So what's next? Why are we doing this technology demonstration? We said we want to do science, but how do we get from where we're at now to where we want to be? Next slide. So since we developed Ingenuity about 2 years ago now, we started something called the Mars Science Helicopter Project, which is a joint effort between Ames and JPL to develop the technology that'll be needed for the next generation of Mars helicopter to do their own science. So what you can see here is a graph of Ingenuity's current capability, which is you have a trade-off between how far you travel, which is range, and the hover time, which is there on the y-axis. And so we, with Ingenuity, can hover for about 1.5 minutes or fly for a range of about 2 kilometers. And so as you see the test flights, we'll kind of start the test flights over the next couple months with doing the hover time, and then we'll start working our way across the range as we do our demonstration flights. Next, please. But it turns out that, you know, technology develops really quickly. And so in the time that we have, you know, finalized the testing and packaged up Ingenuity, we've actually been able to increase the performance of the vehicle significantly. So that means that if we were to redesign and then reship Ingenuity in the exact same form factor and everything today, by this point, you know, we've been able to collect a lot more data and optimize the blades even further, as well as add additional batteries and motor. Means that if we were to ship an advanced version of Ingenuity, instead of being that little red line of performance that's in the corner, that's that same graph of hover time versus range you saw in the previous slide, then we can actually expand the performance to those blue lines. So the blue lines are options of payload sizes. So the far one on the right, the longest one, is if we were to fly the Ingenuity mission exactly as it is, and we could actually now go up to 14 minutes of hover time or go for a range of 32 kilometers, which is a significant increase. Additionally, we could carry up to 1.3 kilograms of dedicated science payload, again, without changing the size or anything of Ingenuity, just, you know, replacing the rotor and adding more batteries. So that's really cool. Next slide, please. As part of the Mars Science Helicopter Project, you know, we're not limited to just further developing the configuration that we have, the vehicle concept that we have. We also generate and test future concepts. And so we've also made bigger versions of the vehicle. You can see that scaled coax, that's the third one over, that's kind of a much larger version of Ingenuity. Then you can also see the hexacopter that's there. And those allow us to really increase our performance. The 2 vehicles on the right are about 20 kilograms, but they can carry up to 2 kilograms of science payload, go 2 kilometers, while also increasing the hover and the range. And the actually really cool thing is that when we switched from that coax design to the hexacopter design, because we weren't continuing to increase the rotor size, which caused extra flapping, we were actually able to keep the vehicle more stable up to this point And so that allowed us to actually increase the vehicle design even further from a performance perspective. So that vehicle on the far right, that's a hexacopter performance, we now have a version that's 31 kilograms that, you know, we added a lot more battery and power into, and we can carry up to 8 kilograms of science payload, which is really, really cool if you remember that Ingenuity itself is only about 2 kilograms. So that means we could carry a science payload that's about 4 times the mass of Ingenuity. Next slide, please. So in addition, so just for some closing marks, we're so excited about Ingenuity, and it's going to be a great first step, but we also have really big things planned. And so with these new science helicopters, we can go, we estimate that we can go the distance in 3 days, the same range that it's taken Ingenuity to travel in 5 years. So that's huge, and we have a lot of science coming down the line for you.
Yeah, I just want to echo Shanna's excitement, and we're going to end this presentation with some closing remarks. So next slide. So the Mars 2020 mission is really a high-risk, high-reward mission. And, Ingenuity is a flight demonstrator. It's going to be the first. But we've done our best to make sure that this Ingenuity can fly in Martian-like conditions on Earth, but the rest is up for time to tell. But regardless of whether Ingenuity will be able to fly or not, the Mars helicopter program is already a winner. So Ingenuity will be the first aircraft to attempt powered control flight on another planet. And furthermore, we have learned a lot about how to get technology up to this spot, and we will learn more when Ingenuity attempts to flight, which will be beneficial to future missions. And lastly, in a lot of ways, Ingenuity mirrors a lot of Wright brothers moments. The Wright brothers airplane was the first aircraft to attempt powered control flight on Earth. And also the Wright brothers airplane's design also had counter-rotating rotors. And lastly, one really cool fact is that, as Shanna mentioned, Ingenuity is planned to perform 5 different flights, and those flights actually parallels the Wright brothers airplanes flights. In those flights, we're going to be looking at a similar elevation and a similar range of flight to the Wright brothers airplanes flight. Next slide. And that concludes our presentation. Thank you so much for having us. We're really excited to speak with you all. We're going to open this to any questions from the audience.
I have a quick question for you. It's actually something one of the audience members asked. There's a lot of fine dust on Mars, and you're going to be working in a very dusty environment. Dust is going to be blown around by the wind, and of course, when the rotors are turning, they're going to generate a lot of dust. What have you done to protect the helicopter from the dust, and will that also cause any problems for the rover itself?
Yeah, so for the helicopter, we actually did a really interesting test where we figured out that the way to simulate the dust blowing up within, Earth's conditions and with the gravity constraints was to use crushed up walnut shells. So there's a really interesting long story of how the engineers got there. But we tested it in that one tunnel facility that we showed you that's also a vacuum with the crushed walnut shells to see if we were going to get those clouds. There's something called brownout that happens a lot when you fly in the desert. That's been a lot of trouble for past helicopter pilots. And so we were able to show that, at least from a brownout perspective, that the cameras and the navigation equipment will not be affected to the degree that they won't be able to fly for these first test flights. And because we're only doing 5 flights, we're not really too concerned with buildup over time or with the blades getting dulled by the sand. But as we go into the more advanced Mars science helicopter designs in the future, that's definitely something that we'll have to implement into the design and things that we're considering because they will be longer missions.
Great.
Fantastic. I know I've learned a lot, and our watchers have learned a lot, and no doubt we have a lot of students who are watching who are inspired by your work and the overall mission. Could you give us a few insights to how you got into this field?
So I was always inspired by NASA's missions, especially the Mars missions. That really inspired me to study engineering in college. As you know, I mentioned, and also Shanna mentioned, we both started off as interns, but the way that got us to get this internship position is by making the most out of our resources in college, joining clubs, doing side projects, doing research. And from that point onwards, doing the internship and doing our best in the internship to make a mark.
That's really inspiring. How about you, Shanna?
Yeah, I'll just echo Winnie's remarks, and that, it's all about, it doesn't matter what your background is or where you come from. It's more about, just pursuing something that you're excited about. So for me, I'm originally from Missouri, and so I didn't grow up with a lot of space influences, directly around me. There is, getting to be more of those influences there, which I'm really excited about, because it's my home. But, I didn't grow up seeing the launches in my backyard or anything. And actually, I'm a first generation college student as well. And so I didn't, grow up with parents that were engineers or anything, but my dad, owns a shop where he fixes cars for a living. And so I grew up around the shop with my dad, and he, taught me from a young age how to, look at something that's wrong and try to figure out how to fix it. And he got me used to working with my hands. And, that kind of made me realize that I enjoy that problem solving aspect and the mechanical problem of like how to fix something and make it work. And so that was a really good background then when I did go into college to apply, to my math classes and things like that. And I ended up, picking engineering because it was kind of a cross between the two. And also I kind of picked this area just because I think it's so fascinating to learn about our universe. And, the more technology we develop, the more and more we learn. And that can really affect, your worldview and motivate you, throughout your life. And that's just really cool. So I wanted to contribute to that. And like Winnie said, taking advantage of those opportunities, just like having conversations with people, other engineers that you come across. Basically, anybody who has gone kind of in the area you want to go, they probably, have advice that they're willing to pass on and talk to you about. There's very, few people who aren't excited to talk about what they work on. And so just having those conversations and, taking advantage of the opportunities that did come up in the internships and things like that is just a really great way to get started.
I got a question for you. Are either of you pilots? And if not, do you plan on flying airplanes and ultimately helicopters?
Yeah, I'm not a pilot, but that's one of, while I was an intern, that's one of the things that I've noticed a lot of interns having that skill. That would be cool if I had that skill.
It's more than a skill. It's incredibly awesome.
I have
so
had
good luck.
The opportunity to fly with another pilot. I don't have a pilot's license, but I will say it was just, extraordinary to have that feeling of being in the air and being in control of the craft, and is definitely something that I would like to pursue in the future again, time allowing. So.
Great. Hey, can your aircraft upright itself if it should tip over? I was curious.
Yeah, so that's a question that we get a lot. Again, Perseverance will wait until we have the best conditions possible to drop it off. And so, the main aspect of this mission is perseverance. So while, like I mentioned, at the beginning of the talk, while the rover group was so kind to, allow us to go ahead and tag along with them and take up some of their mission time, we also, didn't want to make, we didn't have the budget or the time or the space to make the rotorcraft, as completely robust and be able to do all the things that we would like to do long term. So, again, for this, it's more of a piece of science instrumentation. So we're going to do the best that we can with the time that we have. And then in the future, we're looking at things to, design into the landing gear and things like that that could potentially help it if it were to flip over.
One of the questions that came from the audience, I think you said you're going to do 5 flights. Is there a chance that you're going to do any more? Do you have any plans to do any additional missions beyond those 5 flights?
Yeah, so like I said, we're borrowing time from the rover. So hopefully we'll make it through all five missions, but then after that, the rover will move on and do its own mission, the primary mission. And at that point, Ingenuity won't be able to, even if it were able to operate, it won't be able to communicate any data or anything because we're going through the rover to do that. So we will stop flying after the 5 missions.
Oh, okay.
How can missions like Perseverance and Ingenuity get us closer to manned exploration of Mars?
So, we're looking into the future and we're not there yet. So who knows how it will actually go down. And that's one of the really cool things about being a young engineer in the field. And especially when we get to talk to students, it's, I've only been out of school now for, well, actually, I won't tell you exactly how long, but not for that long. And, I'm already getting to contribute to these types of missions. And a lot of the students that I work with have contributed directly to this mission. And so that's really cool because this is a brand new technology field. And it's not like you have to wait 5 or 10 or 15 years to grow up in order to, be involved. So some of, those details will actually be worked out probably by the students who are listening. But kind of in my mind, what I see is, astronauts being able to use the same rotorcraft that we're using to help them go retrieve samples or do really hazardous tasks, things like that, maybe even eventually help with transportation of the astronauts. And as well, we'll be able to use these types of vehicles in the future potentially to, help set up the camp for, the astronauts to get there and just to minimize as much unnecessary work and risk to the astronauts that are there as possible. So we'll see what actually happens, but that's kind of my personal vision.
That's great. We're getting a few more questions about the survival via the windstorms. Could you refresh us on how it's built to withstand all those conditions?
Yeah, so, it's made to withstand wind gusts up to a certain point, but that's why we have the sensors on the rover and on Ingenuity itself, so that if it's above a certain wind speed, we won't fly, we won't take off.
That's great.
So there's a common misconception about wind on Mars. We often hear about the wind speeds on Mars being 100 kilometers per hour or more, and people think of that as being hurricane force winds. Could one of you kind of talk about what the force actually is when you get 100 kilometer per hour wind on Mars?
So to be honest, actually on the engineering side of things, I'm not completely sure about that specific subsystem. That's a little bit outside of my expertise area, but it is less extreme than what you would expect to experience here on Earth. And, we're looking at the future, those don't happen all the time. We have extremes here on Earth, we have extremes here on Mars. And so, things that we can do in the future if we do travel with other landers and rovers and stuff is actually use them as protection as well if we were to encounter those types of situations.
Right. One of the things you got to keep in mind is because the atmosphere is so thin on Mars, 100 kilometer per hour wind on Mars would feel like a light breeze here on Earth. You know, there's a scene in the movie and the book, The Martian, where they talk about 175 kilometer per hour wind, and they show it knocking over structures and things like that. And the 175 kilometer per hour wind on Mars has the same force as a 12 mile per hour wind on the Earth. So it's a lot less strength for the velocity that you hear about.
To expand on that also, if you go in the other direction where you enter an environment where the pressure is greater than 1 atmosphere at sea level, like in a diving bell or pressure chamber for scuba divers. I know from my friend's experience describing it to me that in 4 atmospheres of pressure, everything seems normal, but when you move your hands, you can really feel the thickness of the air. Just sweeping your hand across the air, it takes about 4 times the effort. You can get a workout just doing jumping jacks in that. So
I hear the helicopter has some artificial intelligence for navigation. Can you tell us what it can do?
Yeah, so I can answer this question. I guess one thing to clarify is that flight trajectories for the Mars helicopter has been computed in advance and fed from our team at NASA over to the rover and then over to the Mars helicopter. But you know, autonomous with quotes, because this trajectory has been planned in advance, is necessary because of the delays in communication between Mars and Earth.
Do Ingenuity and Perseverance communicate with each other?
Oh, yes, they do. So, you know, as Ingenuity flies, very crucial information, including the current, the power, and these data is fed over to the rover, which is then fed over to us on Earth, just for us to understand how well its flight performance is in the Mars environment.
Wow, that's amazing.
Mm-hmm.
So going back to the design of the helicopter, why are the blades vertical on top of each other, unlike drones that are at the 4 corners?
Size.
Yeah, so if you think about a helicopter, if you just have like a rotor rotating, there's a lot of angular momentum from this, which is why a lot of helicopters feature a rotor on the tail to counterbalance this. And for the Ingenuity's case, we have counter-rotating rotors that are coaxial. And the reason for this design is that it's compact. And as you've seen in earlier slides and also the live stream, you have the entry, descent, and landing systems, which have its own packaging constraints. How can we fit a spacecraft inside the belly of the rover, which actually has, you know, limited size? So this compact design allows us to efficiently fit this helicopter inside the rover.
Here's a question for the whole team. How much of a role did NASA geologists play in selecting the landing site? And are there any onboard instruments to analyze core samples in advance of the return to Earth?
I'll take a first stab and then maybe somebody else can add on. So the process for determining site selection is actually really cool. Like I said, at NASA, it's all about collaboration. And so one of the things that we do is to do a site selection when you're proposing a mission is you get a team of, you know, literally it can be up to like 100 experts in a room. You know, you try to keep it small enough so that it's a productive discussion, but you bring together a group of experts that are from all the different fields, from, you know, geology and the EDL experts, the entry, descent, landing experts, and the vehicle experts, and they all have input. And so, everybody kind of brainstorms some ideas, throws locations out there, and then everybody kind of gets, a semi-equal vote of, to say, I think this would be really good, but here's the challenges. So the engineers get their chance to talk, and the scientists gets their chance to talk, and then everybody kind of, ranks them as a team. And so, depending on the particular challenges of the mission, you might hear from the geologist more, or you might, hear from one of the biologists more, depending on what you're trying to do.
As we approach the hour here and we're running out of our time, what advice would you give to students who want to follow in your footsteps? Everybody. Fareed has a book there. Physics.
No, be curious. I mean, that's it. Just be curious, Don't just walk around and kind of see things and, whatever they are is what they are. Actually ask yourself, why are things the way they are? What causes things to happen around you in your environment? And I think curiosity is probably the greatest attribute that you find in scientists. They want to know why things are and how things work.
Yeah, I mean, just echoing off of that, the names of the rovers are really indicative with curiosity and perseverance. It's, again, not about the background you come from, but just finding something that you're excited about and being willing to take the initiative to look into it and learn about it. And, you don't have to have a ton of resources. If you have a library, if you have a Google connection, there's so many resources out there and available to you, especially now that we've, started doing so much telework. That really stinks for a lot of people. But one of the things that has been good about that is that resources are continuously getting pushed out for students to be able to teach themselves remotely. And that's just really, really cool and really enabling. So, find something that interests you, and then don't be afraid to ask questions about it. If you get stuck on a problem, go find a teacher to ask. And, if your teacher doesn't know, they can probably help you find somebody who can. And so, yeah, just take that initiative.
Yeah, I'm going to add on to this. Find ways to challenge yourself. Work on a project. If you're really curious about this, it's very good that you make sure that you're good on your fundamentals. And if you don't feel challenged enough, try to find ways to challenge yourself by exploring more advanced concepts and such. I think one thing a trait that's very valuable anywhere that will get you through many things is just having self-motivation and perseverance. Because times do get tough. When you feel challenged, that's when you grow the most.
That's great advice. I want to thank you all for joining us. The conversation continues. So if you haven't had enough of Mars, join us tomorrow morning at 11 a.m. We'll have Jose Santos from NASA, aerospace engineer, and we'll be talking about the descent, arrival, and the landing once again in greater detail. So I want to thank you all for joining us. Today is a success, but the mission isn't over. So keep looking up and out there. We'll see you next time. Bye, everybody.